Okay, good morning, everybody. So today we'll have a uphill battle, and that is to finish module number 4. Na super mainitin it might. I think I finished writing it kanina mga 4 a.m. I have a very bad working habit, and I'm working on trying to make it better. Ginamit ko na yung SS ko o dun sa mga hindi gamers dyan, yung mga ultimate skill ko na cramming. All right. So I think I work best under pressure. So kailangan ko antayin yung deadline para matapos talaga for sure yung isang bagay. So, but I don't think that works for everybody. That works for me. I don't know for you guys, pero wag niyo akong gayahin. All right. Okay, so saan nga tayo natapos last time? I think we finished describing Euler's method. And then, aling example ang natapos natin? Natapos ba natin yung tatlong examples? Tandaan niyo ba? In that example, we have one function. So isa lang function yung kino-consider natin, and we're trying to find its roots because the promise of Euler's method is that it can give us complex roots. And it was a nice extension of the secant method, a very simple one, pero yung nadagdag niyang capability dun sa secant method is very profound. So nabigyan tayo ng paraan para mahanap yung mga complex roots ng isang mga nung mga functions by just simply replacing the secant line dun sa secant method by the interpolating quadratic polynomial in Euler's method. Okay? And then yun nga, ang ganda nung nakuha nating additional feature using Euler's method. Okay? And in example 4.1, I did 3 instances of Euler's method starting with 3 initial triples. Okay? So, dito nakuha ko yata yung real root. Dun sa pangalawa, nakuha ko yung isang complex root or isang non-real root. And I hope I mentioned last time the complex conjugate theorem. Kapag meron kang polynomial, pag meron kang polynomial, tapos meron kang complex number z, which is a plus bi halimbawa, na root niya, automatic yung conjugate nitong complex number na to, which is basically you just flip the sign of the imaginary part, is also a root of the polynomial equation. Okay? But again, true lang to sa mga polynomial equations or polynomial functions. So, laging yung mga non-real roots, they come in complex conjugate pairs. Okay? So, paglaruan, yung initial conditions, makakakuha tayo ng iba't ibang mga roots. Okay? So, and then I know some of you started writing the code for Euler's method and try to answer example 4.1 and try to come up with the other 2 real roots of the function f we considered in example 4.1 using Euler's method. Tapos pag medyo ginaganahan kayo, you can go ahead and try exercise 4.2. Okay? Now, okay, so yun yung kagandahan ng Euler's method. The thing about Euler's method also is it surprisingly converges faster than secant method. Remember, we knew that the secant method converged at a rate of 1.618, about 1.618, the golden ratio phi. Okay, pero yung Euler's method, interestingly, mas mabilis yung convergence niya sa secant method. Kasi nga, it was shown by, I guess, it was Euler who was able to prove that the rate of convergence of his method is 1.84, together with this estimate for the asymptotic error constant. Okay, but bakit mas mabilis siya than secant method? Number one, for the convergence of the Euler's method, kailangan ay thrice continuous yung function. So continuous si function, continuous si f, at saka continuous si f prime. Si f prime, si f double prime. Okay? So, and also f, tama ba? Thrice continuous na siya. So dapat continuous yung mga derivatives na yun. Okay? So basically, mas marami itong requirements para sa convergence kesa sa secant method. Okay? But it is It is subquadratic, so mas mabilis pa rin yung Newton-Raphson method. Okay. But yun pala, we need to be a little bit careful when talking about um, yung pagiging fast ng isang algorithm, because we can describe, we can use fast as an adjective for two things. Number one, the rate of convergence. So pag sinabi natin mas mabilis yung rate of convergence, meaning it will take less number of iterations before a certain stopping criterion is met. Okay? So pag sinabi natin mas mabilis yung convergence, ang tinitingnan natin ilang iterations yung kailangan, right? Ilang terms dun sa sequence of estimates yung kailangan para ma-meet natin yung stopping criterion. Okay? And meron pang isa, yung pagiging mabilis with respect to the running time or the CPU time or physical time. Okay? Now, I am very happy to see some of the works of my D2L students. Shout out to you guys. All right. Na merong mga certain examples or merong ilang instances ng problems sa kinonsider natin in the previous lab exercises na okay, mas mabilis yung convergence ng secant method kesa doon sa mas mabilis yung of course, mas mabilis yung convergence ng Newton-Raphson kesa sa secant method, all right? So it will take 2 less or 3 less iterations for the Newton-Raphson method to converge than the secant method, okay? Pero nung tinali nung ilang mga students yung running time, nakita nila na mas mabilis yung pag-run nung secant method physically on the CPU than the Newton-Raphson method. So even though mas mabilis yung convergence ng Newton-Raphson, mas mabilis yung running time ng secant. And I think I briefly touched on this last time because the Newton-Raphson requires computations of two different function values at every iteration. Actually, not just two different function values, but the calculations will involve two different functions, f and f prime. Meanwhile, the secant method can be programmed in an efficient way so that only one function value evaluation is to be done at every step. Actually, kahit nga hindi ka magtipid sa function evaluation, kapag ka yung function ay may komplikadong derivative, edi may mas edge na si secant method kasi mas madaling mag-compute ng f kaysa kay f prime for most cases. Okay? So, yon, be careful, lalo na sa problem set. When I ask you a conceptual question, you just can't say the secant method is faster or the Newton-Raphson method is faster than the secant method. You need to qualify ano yung object ng adjective na fast or faster. Okay? So, be careful about those. Okay? Now, yun yung kasing price that the Newton-Raphson method had to pay to gain quadratic convergence, because I mentioned last time na napaka-rare na mga methods that have quadratic convergence. So kailangan niyang i-give up yung operation count. So it needs to admit more operation count or more complicated calculations every iteration to attain a fast convergence. Okay. And most of the time, especially for complicated functions that will take thousands of iterations to produce a sequence of good estimates, all right, it is a good price to pay. It's a good bargain. But of course, in the real world, walang free lunch. You have to give something in order to gain something. So yung pagkaka-gain ni Newton-Raphson ng quadratic convergence came at the price of more calculations at every step. Okay. So kumbaga sa Full Metal Alchemist, yan yung law of equivalent exchange. You cannot gain something if you are not if you will not give up something in return. So parang ganun yun. Okay. So off script na naman ako, ang dami ko dapat gawin today, pero yon. So that's I think that's the end of Mueller's method. We will not look at the proof of the convergence. Actually, mahirap daanan yung mga proof ng convergence, lalo na kapag ka irrational yung rate of convergence, kasi maraming analysis ang mangyayari, maraming approximations. There might be some results that we need to use. So we'll just believe Mueller. Actually, nilagay ko dyan yung reference kung saan may proof, okay? I don't expect you guys to read it, pero this is just for me to read later. Baka naman kaya kong i-rephrase yung proof niya para sa undergraduate audience, okay? So that's Mueller's method. So though Mueller's method can give us complex roots, meron itong ilang problema. Una, tatlo yung kailangan nating initial values. Okay? Tapos, um, para mag-converge yung Mueller's method sa isang specific root nating hinahanap, especially if you want to tailor fit it to get complex roots. Kasi nga, kung hindi naman tayo interested sa complex roots, then we can do Newton or we can do secant method. Alright? So, kailangan piliin natin ng maayos yung initial values. Kailangan it should be cooked up in a manner na doon talaga siya magko-converge sa complex root. And it would be difficult kasi nga wala tayong way para malaman yung neighborhood kung nasan yung complex root. Because the only tool that we have so far to guess where a root lie ay sketch yung graph. Okay? So unless mag-graph ka over the complex plane which is hard to visualize, okay? Mahirap mag-shop ng initial conditions to get the wanted complex root. So it's like searching for a needle in a haystack. So mahirap mag-cook up ng initial values, right? And if you tried doing exercise 4.1, which is basically looking for the two other roots, may nagtry ba? Kasi nung nagtry ako, although mali pa nun yung Matlab code ko, nahirapan akong hanapin yung dalawang natitirang real roots. Yeah, probably it's because my Matlab code was messed up last time. So kaya kahit piliin ko na malapit dun sa dalawang roots na nakita ko graphically, hindi siya nagko-converge doon. Hindi ko pa siya na-try uli. Pero usually mahirap kasi yun nga, para mahanap mo yung ibang roots, kailangan i-rerun mo yung algorithm, use a different set of initial conditions because that's the only way we can influence the method to get the roots that we wanted. So yun yung isa sa mga gusto nating address para paano naman kapag gusto ko makita lahat ng roots ng isang nonlinear function. Okay? Now, generally, it's a very difficult type. It's an Herculean task kasi napakahirap talaga i-predict yung behavior ng mga nonlinear functions. Much more to find all of its roots. Kasi nga, hindi necessarily finite yung roots ng isang nonlinear function, okay? Tapos yun nga, ang hirap niyang i-predict yung kanyang behavior. So generally, it's a very difficult area of research to develop methods to get multiple roots of a function. Yun nga, in my PhD studies, I need to solve for thousands of solutions to a transcendental equation. All right? So kasi kailangan ko siya para ma-compute yung paano nagpro-propagate yung sound sa isang ocean of two homogeneous layers. So kailangan ko yung maraming roots and I need the roots in increasing order. Kaya lang wala talaga akong mahanap sa literature that can find the multiple roots in succession. So alam niyo yung ginawa ko, nagmano-mano ako. So instead of thousands, luckily, na-gain ko yung convergence ng aking infinite series by just taking hundreds of roots. But imagine the painstaking process of sketching the graph of my function over small windows kasi kailangan increasing order. Wala ako dapat maligtangan. Alright? Pwede ako magligtang sa padulo. Pero dapat makuha ko yung first root, second root, third root, fourth root, fifth root, hanggang 100th root. Okay? Kasi sila yung mga roots na nagmamatter dun sa expansion ko. And interestingly, wala talaga akong mahanap na method. Kaya alam niyo yung ginawa ko? Nag-graph ako sa maliliit na windows para malaman kung saan may real root. At least na-prove ko na lahat ng roots ay real. Kasi kung yung mga roots ay may complex roots, disaster. Okay? Hindi ko ma-prove yung, hindi ako makakagawa ng numerical simulation. Tapos sa bawat maliit na interval, kung saan sure ako may root, nag-run ako ng Newton-Raphson. Tapos, ang initial condition ko, malapit dun sa root na alam ko nandun sa interval na yon. Ginawa ko siya 100 times. Okay? So siguro mga 5 hours or more bago ko natapos yung paghahanap pala ng roots, tapos i-input ko pa siya sa isang program na nagra-run overnight. So ganun kahirap. Okay? Pero for us today, we'll continue a simpler version of this problem by considering only polynomials. Okay? Yung mga polynomial functions. Paano natin mahanap lahat ng mga roots ng isang polynomial function? And this is easier because number one, polynomials are the idea ideal functions. They are very easy to manipulate. Tapos marami tayong mga tools from algebra na pwede nating gamitin. Specifically, we have the fundamental theorem of algebra, which tells us that if you have a polynomial of degree n, then it will have at most n roots up to multiplicity. So we know how many roots we are looking for. Okay? Tapos, ano pa nga ba? Well, there's another theorem that I will recall to you, yung factor theorem. Okay? So may dalawang paraan tayong titingnan, pero they go hand in hand. Una, yung generic ay yung deflation method. Okay? Tapos pangalawa yung Bairstow's method na i-couple natin with deflation. Okay? Unahin natin yung deflation because you can use deflation method with in conjunction with Mueller's method and any other method. Okay? Pero ideal gamitin yung deflation kapag to start with or ideal siyang gamitin with a method that can do or that can find complex roots. Makita nyo later kung bakit. Right, first things first. What is deflation? When we say deflation, papababain lang natin yung degree ng isang polynomial. Okay? So we are trying to devise a clever way to find all the roots of a polynomial. So ang gagawin ko ay at every step or at every rerun of the algorithm, instead of running my root finding algorithm, say Mueller's method, in the original function over and over again with different initial values, ang gagawin ko, okay, run ako na Mueller, tapos may makukuha akong root, gagamitin ko yung root na yon to deflate the original polynomial. Ibig sabihin, pabababain ko yung degree ng original polynomial by capitalizing with the factor theorem, okay? Tapos, yung deflated polynomial na, sa kanya ko gagamitin si Mueller's method para makuha ko yung mga natitirang roots. Instead of magra-run lang ako ng Mueller over and over again to the same polynomial with different initial conditions. Okay? Now, paano natin magagamit yung factor theorem in deflation? Well, this is what the factor theorem says. A real number r is a root of a polynomial p if and only if x minus r is a factor of p. And actually, it's not hard to imagine, right? Kasi nga, para maging root, ibig sabihin ng f of r dapat ay equal kay 0. Then the zero property ng algebraic structures o ng fields, ibig sabihin nito, pag nag-plug in ka ng r dun sa expression for f, dapat mag-0. Pero nakakakuha ka lang naman ng 0 if 0 is a factor of f. So, ibig sabihin si f of x, pwede mo palang isulat as x minus r times another polynomial, say q of r. Okay? So nangyayari to kapag ka si r ay factor ni, kapag ka si r ay root ni f. Necessarily, x minus r is a factor of your polynomial f. Now, q is the deflation or is a deflation of the polynomial f. Kasi kung si f ay degree n, pag nag-factor ka ng x minus r, edi si q degree n minus 1 na lamang. So we call q a deflation of the function f. So pag may nahanap ka ng isang root, okay? Pag may nahanap ka ng isang root, pwede mong i-divide yung polynomial f by that factor x minus r, okay? Makakuha ka ng eksaktong polynomial q as the quotient. Zero remainder kasi nga factor siya. Tapos, pwedeng dito ka na mag-run ulit ng Mueller's method. Okay? So kahit nga ulitin mo na yung initial condition na ginamit mo na doon sa previous iteration. Kasi natanggal mo na yung factor na x minus r. So the root r that you got from your previous run of Mueller's method will not appear as the root for q except if it is a root of multiplicity greater than 1. Okay? So ang idea, computin mo si q, okay, which is this quotient, tapos dito ka na mag-run ng Mueller's method. You don't need to change your initial condition or your initial guess. Pwedeng yun na rin yung initial guess mo. Pag nag-conversion, then you get another root. Okay? So, hindi mo makukuha pa ulit-ulit yung isang root r star, okay, o yung isang root r unless siya ay root of multiplicity greater than 1. Okay? And that's basically the idea behind the deflation. Okay? Pero di ba nakukuha lang natin sa mga root finding techniques ay estimates. So halimbawa, R star, yung nakuha nating estimate dun sa ating say Euler's method. So para ma-deflate yung polynomial, perform nyo lang yung long division ng f of x over x minus r star. Okay? And then of course, since this is not an exact root, okay? So posibleng yung division na to will result to a quotient q and the remainder r. Okay? Pero thanks to the continuity of the polynomial f, and as long as r star is close to r, then this polynomial r of x, this remainder r of x, will have norm very close to zero, so small that it is insignificant, na pwede na natin siyang ignore. So in this case, kapag ka maganda talaga yung root mo, magiging maliit yung remainder, pwede natin siyang i-ignore. So yung deflated polynomial, which would be 1 degree less than the original polynomial f, siya yung quotient. Isa-set natin to be the quotient, tawagin natin siyang f sub negative 1. Yung subscript, ayan yan yung degree na nabawas. So from degree n, si q dapat degree n minus 1. Nabawasan na siya ng isang degree. Okay. And then, we run our root finding technique, like Euler's method, on the polynomial q, and we repeat the process until f is down to a polynomial of degree 2 or degree 1. Pagka si f ay na-deflate na natin into a quadratic polynomial, then pwede ka na mag-quadratic formula para ma-compute para mahanap yung natitirang dalawang roots. Kung siya ay linear, then okay. Kasi madali lang i-solve yung solutions ng linear equations. We have the linear formula for that. Okay? Kung cubic, halimbawa nag-deflate ka, tapos cubic yung kinalabasan, you have the option to use the cubic formula. Pero for some reasons, hindi tinuturo sa atin yung cubic formula. Though marami lang radicals, pero it's workable, it's programmable. Pero pwede ka pa rin mag-deflation na lang uli dun sa cubic polynomial. Okay? So, to take full advantage of the deflation process, use a root finding algorithm that can detect non-real roots. Okay? Para hindi ma-disregard yung mga complex solutions ng ating given equation f of x equals 0. Okay? So does the deflation process make sense, guys? Okay? Right. So magiging problema siguro dito yung long division. So if you will allow me, marami bang may klase ng 1 p.m.? Sorry. Because I can give you extra 30 minutes and I can show you my Matlab code para dito kasi baka maging masyadong, sorry, maging komplikado yung programming para matulungan kayo. Lalo na yung iba ay estudyante ko yata sa 155, nagpa-problem set sila. So gusto ko silang tulungan ng konti para dun sa susunod na lab. So if you guys can stick around after 1 p.m. or you can just watch the recording later, I can guide you with the entire process. Okay? So tingnan natin muna yung resulta ng pag-run ko nitong deflation algorithm. Pero i-couple ko yung deflation or I will couple the Euler's method with deflation process. Okay? So yun yung gagawin ko sa example 4.2. So I consider again the polynomial we have in example 4.1, and then I'll take advantage of the previous results we have from Euler's method to identify or to find all the other roots. Because the fundamental theorem of algebra tells us na meron dapat 5 roots tayo makukuha, 5 complex roots up to multiplicity. Okay? So from example A, nakuha natin yung R1 star to be this guy. Okay? Yan yung una nating estimate para dun sa root. Meron yung imaginary part pero super liit. So sabi ko last time, since the imaginary part is very, very small, it's 10 to the minus 16, I think. Pwede na natin siyang ignore. So isipin natin real root yung nakuha ko. So nakuha ko na si R1 star to be around 1.20. Okay? So i-deflate ko ngayon si polynomial f. Dahil meron na akong isang root, kaya kong i-deflate si f by 1 order or by 1 degree by dividing it with x minus r sub 1 star by the factor theorem. Okay? And if I ask Matlab to compute to find the quotient. Okay, syempre hindi ko yan minano-mano, though kung gusto nyo talaga, pwede kayong mag-synthetic division, mano-mano, that's fine. Okay, ito yung nakuha ko mula kay Matlab. Okay, so now I'll call it f sub minus 1 kasi nabawasan ng isang degree mula yung original polynomial. Okay, tapos ngayon, ideally, eto ng quartic polynomial, eto na yung iraran ko ulit, or eto na yung ilalagay ko dun sa Euler's method para mahanap yung natitirang 4 na roots. Okay? So ganun yung idea. Pero hindi ko muna gagawin yon kasi sayang naman yung dalawa pang results na nakuha natin mula kay Euler. Okay? So, or by the way, chinek ko rin nga pala kasi approximate root lang ito, si x minus r1, approximate factor. Kasi nga si r1 star ay approximate root lamang. Okay? Tinignan ko yung remainder. Yung remainder, napakaliit na niya. So, I think it is negligible. So, it's safe to say we can just ignore it and really run the algorithm for this guy. And we're hoping that the small error, that the error in the estimate for r, okay, is small enough and f is continuous enough na maliit na yung remainder. So yun yung hope natin dito sa deflation process. Okay? So mukhang maliit naman to sufficiently. So yeah, pwede kong consider si f sub negative 1. Pero binalikan ko yung example ko uli kay sa 4.1. Nakita ko meron pa nga pala tayong dalawang roots na nakita pa ron. Okay? Dalawa kasi with the aid of with the complex conjugate theorem. All right? So dun sa example B, nakuha ko tong value na to. Itong non-real root R2 star. Okay? Pero sabi ng complex conjugate theorem, kung meron kang complex number, yung conjugate niya ay root din. So ang notation natin sa conjugate ay may bar lang sa ibabaw. So pinaltan ko lang yung imaginary part na to o yung sign na to, ginawa ko lang minus para makuha yung R2 bar star. Okay? So now I'm sure that x minus R2 star and x minus R2 star bar ay parehas factors or approximate factors ni f sub negative 1. Okay? So that means I can deflate the polynomial further by 2 more degrees kasi meron akong alam na dalawang factors. So ganun yung pinagawa ko uli kay Matlab. So yung deflated polynomial f sub negative 1, dinivide ko siya netong quadratic factor neto. And luckily, actually hindi naman luckily, pero expectedly, all right, yung degree for polynomial that is f sub negative 1 after division by a quadratic of polynomial will just become this quadratic polynomial. Ito yung f sub negative 3, deflated by 3 degrees. And I'm very happy with this result kasi pwede ko nang itigil yung ginagawa ko kasi simple quadratic formula na lamang will give me the roots of f sub negative 3. Okay, but before going there, I was a little bit curious and I want to see what's the remainder if it's very small enough. And ito yung nakuha kong remainder. Sabi ni Matlab, ito yung remainder, r, after dividing f sub negative 1 by the quadratic factor from the conjugate pairs, which I think is small enough. So I went ahead and applied quadratic formula and got these two guys as my estimates. Okay, so see 1.65 and negative 2.17, which makes sense by looking at the graph of the function f from example 4.1. Okay? Tapos, sige, nanigurado pa ako, double check. Ano yung function value ng dalawang approximate roots na to, ni R4 at saka ni R5 star. And true enough, they are of order 10 to the negative 9 and 10 to the negative 7, respectively, which is in line with the stopping criterion that we have, or the epsilon we have, which is 10 to the minus 6. Though, yung stopping criterion kong ginamit ay jump-based. Okay? So that's the deflation process. So yung concept, but at least yung concept, does it make sense? Because I understand the programming might be a different case. Siguro inabot ako ng mga 30-minute or 1 hour para mag-program nito. Hindi, actually kasama yung Bairstows. Tapos nag-search pa ako paano mag long division kay Matlab, which apparently is not that difficult. So thankfully, merong Matlab tool, ano? So and then yun nga, for the methods we considered this week, dapat marunong mag-complex arithmetic yung programming language nyo. So sorry for the Excel stance here, okay? So baka kailangan nyo mag-migrate to either Matlab or Python or anything that understands complex arithmetic, okay? All right. So if there are no questions, I'll leave you example exercise 4.3. Okay. So find the roots of the polynomial p using Euler's method with deflation. Okay. I guess ang root nito ay ano nga bang roots nito? Plus or minus 1, plus or minus I, at saka 1 plus or minus. Anyway, I don't want to guess na. So nakalimutan ko na yung roots nito. Anim yung distinct roots nito. Dalawang real, tapos apat na complex, all right? Tapos syempre, essentially dalawa lang yung kailangan yung mahanap na complex kasi nga they will always come in complex conjugate pairs. All right. So if there are no questions with the deflation process, now let's talk about Bairstow's method. Okay. Bairstow's method is apparently much older than Mueller's method. Tama ka ba? Mueller's is 1957. Bairstow's method is earlier in 1920. It was developed by Leonard Bairstow. Pero ang kakaiba ay nasa appendix lang to niyang applied aerodynamics. So I'm guessing, though I'm not sure, kailangan kong i-check, pero kung nasa appendix yan, ibig sabihin hindi siya yung parang star ng libro. Alright? Hindi siya talaga yung main event dun sa book. So, siguro ginamit to ni Bairstow para ma-solve yung mga problems niya in applied aerodynamics. The nice thing about Bairstow's method is that it's an efficient method for finding the roots of a polynomial p with real coefficients. Tapos, ang kagandahan nito ay, ang advantage niya siguro over Mueller's method ay at every step of the way, we get two approximate roots. And those two approximate roots may be complex. Alright? Kasi nga sa Bairstow's, sa Mueller's, isa lang ng isa yung nakukuha natin per run. Okay? Sa Bairstow's, dalawa ng dalawa yung nakukuha natin. Alright? And this will work well with the deflation process. Kasi at every step of the way, after running Bairstow's algorithm, lagi tayong may makukuhang dalawang roots kagad, so we can deflate the polynomial by 2 degrees at a given time. So mas mabilis nating maibababa yung degree ng polynomial na pinaglalaruan natin down to a quadratic or to a linear deflated polynomial. Okay? Now, paano ito nagagawa ni Bairstow? Okay? Ang ginagawa niya ay actually nanguhula siya ng quadratic factor. So, ito yung sinabi ko kanina na nililimit na natin yung pagko-consider natin ng nonlinear equations to polynomial equations. Kasi yung general problem, napakahirap niyang isolve. So, Bairstow's methods works well for, or actually will work only for polynomials. Kasi ang design ng polynomial ng method na to, nanguhula siya ng quadratic factor para dun sa polynomial p. Alright? So, nag-iterate siya, naghahanap siya ng polynomial factor, tapos pagka nakuha niya na yung nice enough polynomial factor or a nice approximate to one of the polynomial factors of p, magka-quadratic polynomial na lang si Bairstow para ma-compute yung dalawang roots ng isang anong given polynomial. Tapos pag nakakuha ka na ng dalawang roots, yung quadratic factor na nakuha natin mula kay Bairstow, okay, mula dun sa algorithm niya, yun yung gagamitin natin para ma-deflate yung original polynomial p by 2 degrees. Alright? Tapos ang isa pang maganda rito, makita nyo ang bilis ng convergence paghahanap ng quadratic factor. So pwede palang ituro yung factoring, no, na yung factoring sa Math 17 o sa high school algebra nyo using Bairstow's algorithm. Hindi ka na magfo-FOIL method, magagawa ng 2 sets of parentheses. Mag-Bairstow's method na lang tayo kasi nanguhula siya ng quadratic factor para sa isang polynomial. So let's do the math. Let's see how Bairstow invented this method or how he developed this method. Okay. So, una, let's consider a polynomial p of degree greater than 3. Okay. So, kunwari, ito yung polynomial. So, at least polynomial of degree 4 yan. Actually, ideally, at least degree 5. Kasi pag degree 4, kaya natin yung isolve using a formula. So, meron tayong quartic formula. Pero starting at degree 5, wala nang generic formula na mag-work. Okay? So, assume natin si P ay polynomial of degree greater than 3. So, from here, makukuha niyo yung mga a sub i's. Okay? The a sub i's are the coefficients of the polynomial, and they are all assumed to be real. So si a0, ito yung constant term. Si a sub 1, siya yung coefficient ni x. Si a sub 2, coefficient ni x squared, and so on. A sub n, x to the power n. Okay? So kailanganin natin ito sa program mamaya. So kailangan yung kunin yung mga a sub k's. Ano yung mga coefficients. Okay? Tapos, ang goal natin ay makahanap ng isang quadratic factor which will be of the form x squared plus ux plus v. Okay? So yan yung goal natin. Mahanap ano yung quadratic factor d. Now, of course, u and v are unknown. So u and v are unknown. Ang goal ng Bairstow's algorithm, hanapin ano yung u and v so that d is close enough to a quadratic factor. Okay? So, paano natin siya mahanap? We have to build up a system of equation or a system of equations to find u and v. Okay. So, paano to ginawa ni Bairstow's? So, pwede tayo, suppose kinuha natin yung division, kinuha natin yung quotient. We divided p by d. All right? So, makukuha natin after the long division or the synthetic division, ipagpalagay natin q plus some remainder. Okay, so meron kang quotient q, meron kang remainder r after division. So we can say that the quotient that we get is say q sub 1, all right, after performing the long division by u, okay? And again, u and v are just unknown constants, okay? So si q1, pwede nating masulat na ganito. So ibig sabihin si q1, siya ay degree n minus 2. So if we started with p of degree n, so si q1 dapat degree n minus 2 siya. Okay. Tapos tawagin natin yung coefficients ay mga b sub k. Alright? Tapos yung remainder r sub 1, kasi nag-divide tayo by a quadratic polynomial, yung remainder at most linear yan. So it's either a linear function or a constant function. So tawagin natin yung linear remainder na cx plus d. Alright? So that is, after this division process, or dun sa mga nag-103, pag ginawa nyo yung division algorithm, okay, si p of x masusulat nyo as d times the quotient q1 plus the remainder r1. Okay? Now, how will you do this? Synthetic division. Pwede nyo siyang gawin. Okay. Now, kailangan ko pa siyang i-divide ng isa pang beses by d. So yung deflated polynomial q1, okay, actually, hindi ako sure na na-deflate pala siya kasi yung remainder hindi ko alam kung close to 0. Because we don't know if really this guy is a good quadratic or is close to a quadratic factor already. Okay? So ang gagawin ko, yung quotient Q1, i-divide ko uli siya by D. Tapos suppose after doing the division, I get the quotient Q2, which would be of degree n minus 4. Kasi si Q1, degree n minus 2, dinivide ko by quadratic, so magkakaroon ako ng degree n minus 4. Tawagin ko yung mga coefficients ni Q2 as f sub k's. Alright? Tapos yung remainder, ipagpalagay natin na qx plus, gx plus h. Alright? So that is Q1 can be written as d, our guess for the quadratic factor, times the quotient Q2 plus the remainder R2. Okay? So yan yung mga relations na meron tayo so far. Tapos ideally, pwede nyong i-carry out yung synthetic division manually. So kung talagang hindi nyo siya ma-program, pwede nyo itong gawin manually. Kaya lang 5 iterations pala yung kailangan ko. So 5 beses ka magsi-synthetic division, which might not be um, very easy to do. Hindi pala. Easy to do siya pero time consuming. So what I did is to carry out the math. Ito yung generic na mangyayari. Pag ginawa niyo yung long division, okay, makakakuha tayo ng recursive equation 4.12 para dun sa mga variables na involved. Hindi ko na ipapakita yung process, pero trust me, nakuha lang to by doing the long division. Okay. Now, una, yung b sub n, remember n is fixed. N is the degree of the original polynomial. Okay? So, fixed na yan. So, sabi rito yung b sub n at saka yung b sub n minus 1 ay equal kay 0. And that's not hard to accept because the b sub k's are the coefficient of the first quotient q1. Pero yung q1 ay degree n minus 2 yan. So, walang coefficient, si x to the n minus 1 at saka si x to the power n. So, ibig sabihin, 0 talaga yung b sub n saka yung b sub n minus 1. Ganun din si f sub n at saka si f sub n minus 1. Kasi si f naman ay yung mga f sub i's, sila naman yung coefficients ng q2 which is of degree n minus 4. Okay? So pwede niyo nga sabihin 0 to hanggang kay f sub n minus 2 at saka kay f sub n minus 3. Okay? Pero this will suffice. So kung i-code nyo to, i-program nyo na to. Kaya lang pabaligtad yung for loop nyo. Back recursive relations kasi yung meron ako. So we start at n and then we go down to define it until k equals 0. Okay? Now this is fine. I-ano nyo lang yan. I-encode nyo lang yan. Or initiate yung value. Tapos si b sub k ay computed this way. Remember yung mga b sub k's, ito yung mga coefficients tung result ng unang synthetic division. Alright? Ito yung coefficients ni q1. Alright? So pag dinivide mo si P by the by our guess for the quadratic factor D, makukuha mong coefficients yung mga BK. Pero yung pagko-compute ng BK, nakadepende siya sa AKs, which is fine because we know all the AKs, they are the coefficients of P, right? Si U ay unknown, okay? Tapos si B sub K plus 1 ay na-compute na before kasi nauuna natin kinompute yung mas matataas na degree. The for loop here should go from n minus 2 down to 0. Okay? Kasi, di ba pag naglo-long division tayo, nauuna natin pinag-divide yung mga matataas yung degree. Kaya nauuna ritong nauuna nating ma-compute yung mga coefficients ng higher degrees. Okay? So si FK, ito rin yung itsura niya. Alright? And again, this is dependent on the unknown U and V. Alright? Tapos si C, ito yung coefficient dun sa remainder. Compute it this way. Si G, nandun din siya sa remainder. Si D nasa remainder. Si H nandun sa remainder. So if you'll write a program for this, make sure to encode these lines in this particular order. Okay? Kasi nga, recursive siya, kailangan ko yung mga previous values para ma-compute yung previous value, yung mga bagong values. So for instance, I cannot compute D and H without computing the BKs and the FKs muna. Alright? So ganun yung siya gagawin. So at this point, kapag alam nyo si U at si V, ano yung U at saka yung V, mako-compute nyo yung coefficients ni Q1, coefficients ni Q2, coefficients ni R1, coefficient ni R2. Mako-compute nyo silang lahat. Okay? That is, if you know U and V. Right? Pero we want U and V to be chosen in a nice way because remember, we want D to be a factor of the polynomial P. Right? So kailan ba si D magiging factor ni P? Alright. So by the factor theorem, D will become, or a consequence of the factor theorem, D will become a factor of P if the remainder is equal to 0. Okay. So, ganun, di ba? Pagka magiging factor siya kapag ginawa mo yung division, tapos ang remainder ay 0. So we want R1 to be 0. So we want U and V to be chosen so that R1 is equal to 0, but R1 will become 0 if both C and D are 0. So yun yung magiging condition natin dito. We want C and D to be both equal to 0. Tas lalabas na yung nakakatakot na equation 4.14. All right? Pero don't be scared of it for now, okay? I-explain ko kung paano yan gawin. Okay. Now, ang problema natin, balikan natin si C and D. Yun lang pala yung kailangan. I-equate ko lang si C at saka si D parehas kay 0. All right? But look at C and D dun sa synthetic division. Nakadepende siya kay U at saka kay V. All right? So again, if we know U and V, then that's fine. We can compute for C and D. But we want the C and D, and we want to find U and V. All right? So medyo inverse problem ito. Alam natin yung output. Gusto ko yung C ay 0. Gusto ko yung D ay 0. Pero ang problema ko, ano yung U at V? So essentially, what we'll do is to treat C and D to be functions of U and V. All right? Function of two variables. Mat38, hello. So nag-high na siya dito. So gusto natin yung C of UV and D of UV ay equal kay 0. Okay? Then, gusto kong i-solve itong system na to. Kaya lang, mahirap siyang i-solve by hand. Okay? So ang gagamitin natin ay mag-Newton-Raphson method tayo. Pero mas high-tech na Newton-Raphson method yung gagamitin natin. Newton-Raphson method in 2 dimensions. Okay? Remember, in 1 dimension, ang Newton-Raphson method ay ito lang. Okay? Yan yung Newton-Raphson in 1 dimension. Pero ngayon, 2 dimensions, so ibig sabihin vectors yung paglalaruan natin. So yung ating estimates, okay, ay magiging vector consisting of 2 entries. Yung unknown U at saka yung value ni U at saka value ni V at the J plus 1 iteration. So yung X natin dito, instead of a real number, will become of 2 vector. Magiging 2 vector na siya. Ito yung mangyayari dyan. Tapos syempre ito, magiging 2 vector din yan. Alright? Tapos function value at xn. Pero saan natin siya ipa-plug? Ipa-plug in natin yung U at saka V kay C at saka kay D respectively. So itong function value na to mapapalitan yan. Okay? Tapos merong division, may division dito F inverse. Ito ay F prime. May division by the derivative. So instead of a division, sinulat ko siya as multiplication by the inverse. Okay? So itong over F prime of x sabihin, napalitan siya nito. So nagkaroon siya ng inverse kasi nga dapat nasa denominator siya. Tapos pag meron kang vector, ang derivative ng isang vector actually ay isang matrix, isang 2x2 matrix. I don't know kung inabot nyo to sa Mat38, pero kapag ka meron kang vector, dinifferentiate mo yung vector, kaya ang sagot doon ay magiging matrix. Ito yung matrix na parang extension ng derivative ng function f. Okay? But of course, nakakatakot yan. Maraming mga partials, naka-invert pa yan. Pero ang kagandahan, 2x2 lamang siya. And then another nice thing is that C and D are simple functions. Okay? Si D nga, wala siyang involved na U, so function lang siya of V. So madaling kunin yung partial ni C with respect to U and with respect to V, ganun din si D. So madaling mapa-plug in ito, alright? Tapos 2x2 yan, madaling kunan ng inverse yung 2x2 matrix. And actually, I did the math, kinompute ko na ito para sa inyo, hindi na kayo mahirapan or matakot mag-partial. Ito na yung nakuha ko. Example, equation 4.15. Okay? So ito ay yung usual vector iterate, yung previous iterate. Tapos minus this guy, ito yung determinant nung inverse nito. Okay. Tapos siya yung determinant nito. Okay. Tapos matrix lang to of some constants, all right? Times CD. Okay. So this is a matrix, this is a vector, this is 2x2. This is 2 by 1, so this matrix product is well defined. Tapos ito ay magiging 2 by 1 times a constant, so 2 by 1 pa rin, 2 by 1 minus 2 by 1, 2 by 1 pa rin. So the dimensions will agree. Okay? So familiar naman kayo sa matrix multiplication, no? Sa matrix algebra. So you just need to encode 4.15. So maraming encoding na magaganap. Kasi nga, mangyayari, mag-Newton-Raphson tayo yung extension niya into 2 dimensions para mahanap si U at saka si V. Now, of course, you will give an initial guess for U and V. Kailangan mo ng U0 at V0. Pag meron ka ng initial guess kay U0 at V0, ipakompute mo ito ngayon kay Matlab. Yung mga coefficients na yan. Okay? Kukompute ni Matlab yung mga coefficients na yan. Pag na-compute na ni Matlab yung mga coefficients na yan, kaya mo nang computein ito. Alright? So initial guess minus all of these guys, but V will be replaced by V sub 0, U will be replaced by U sub 0. Okay? Yun pala yung mali ko rito. Dapat ito ay VJ, ito ay UJ, VJ, UJ. So yun yung mga initial guesses. Alright? Tapos lahat ng mga natitirang constants dito will be computed using the relation in example 4.12. Okay? So, kukunin niyo yan. Tapos, may makuha ka na U1 at saka V1. Okay? But you will need to check kung okay na ba yung U1 at saka si V1. Paano natin i-check kung okay na siya? Gamitin uli natin yung jump-based stopping criterion. Okay? Ninote ko ba yun dito? Okay. Dun yata sa example ko siya ninote. Typo uli. Sorry, madaling araw na yan nagawa. Marami pa ring typos. I'll correct it later. Okay? So, para malaman kung pwede ka nang tumigil, kunin mo yung relative jump dun sa mga U's, tapos yung relative jump dun sa mga V's. Pag parehas na silang less than epsilon, then tumigil ka na. So, kung si U1 ay hindi pa ganon kalayo mula kay U0, si V1 di pa ganon kalayo kay U0, or at least one of them doesn't meet the jump-based stopping criterion, then we give it another go. Okay? So, pag natapos yung run mo dito, meron ka ng U1 at saka V1. Kailangan mo pang mag-go kasi hindi mo pa na-satisfy yung stopping criterion, babalik ka na naman from the top. So, using U1 and V1, kukomputin mo na naman itong mga coefficients na to. Tapos, pag na-compute mo na yung mga coefficients na yan, Newton-Raphson. Okay? Makukuha mo naman si U2 at saka si V2. Check stopping criterion are met. If not yet, then go back to computing all of these coefficients, another batch of Newton-Raphson, and so on. The nice thing about Bairstow's method is that it inherits the quadratic convergence ng Newton-Raphson. Okay? So, ganun siya kabilis dapat magko-converge. So, it won't take you 10 iterations to meet a stopping criterion of 10 to the minus 6. Mabilis talaga to kasi Newton-Raphson method ito, quadratic convergence. Okay? Now, okay, kunwari natapos na. Meron kang U star at saka V star. So, ibig sabihin, yung D natin, which is defined this way, x squared plus U star x plus V star, okay, is close to a quadratic factor of the polynomial P. So therefore, to get our first two estimates for the roots, all right, or our, all we need to do is to apply the quadratic formula here. Okay? So ang A mo ay 1, ang B mo ay U star, tapos ang C mo ay V star, quadratic formula will give you your first two estimate for the roots. Okay? Tapos yun nga, pwedeng complex yung roots na makuha mo kasi nga quadratic formula yung ginagamit natin. And then instead of rerunning Bairstow's algorithm with a different choice for U star and V star, ang gawin mo, i-deflate mo muna yung polynomial P para hindi mo na ma-encounter yung same roots na nakuha na natin kung sila ay hindi multiplicity of more than one. Okay? Para hindi siya ma-replay. Alright? So, i-divide mo si P by the supposed factor D, all right, para makuha natin yung actual solution. Okay? So, do you guys get the process? Ito pala, mag-overtime na ako. So, if you guys have classes, so you can go, all right? Just watch the recording later. But if you can stay, it will be great para may kausap man ako, para may kausap ako or may nakikita akong mga DPs, all right? Ay tutuloy ko, tatapusin ko siguro to para mapakita ko rin yung code. All right? Okay lang ba? All right. Pero kung kaya niyo naman siyang i-code, then yeah, okay na. Bye-bye na. All right? So, pero gusto kong i-present yung code. Yun yung idea. Okay? Sige, ano kaya maganda? Okay, sige. Gamitin ko yung program ko. Nag-open na ba si Matlab? Yeah. Para gawin tong example 4.3. Para i-illustrate sa inyo yung nangyayari. Okay. Now, in example 4.3, we want 4.3 ba? Siguro gawin ko na yung sige, 4.3. Okay, 4.3. Gusto ko i-consider yung Gusto ko i-consider yung x to the fourth minus x minus 10 using Bairstow's method with deflation. Okay? Yun nga, ang advantage ng Bairstow's at every run of Bairstow's algorithm will get two roots. Tapos, ang bilis nating makukuha yung dalawang roots na yon kasi quadratic yung convergence. Compared to Mueller's, na isa lang yung nakukuha nating root at any given run and ang convergence niya ay ang convergence rate niya ay 1.84 lamang. So, mas mabilis talaga yung Bairstow's. Okay? Now, okay. So, ito yung problem natin. Tapos ang stopping criterion, ang epsilon ay 10 to the negative 6. Una kong kailangang hanapin ay humanap ng estimate para kay initial guess para kay U0 at saka kay V0. Right? Remember, they will be our initial guess for the quadratic factor D. Tawagin mo siyang D sub 0, initial guess. Siya yung x squared plus U0x plus V0. Okay? Ito yung magiging initial guess ko dun sa two-dimensional Newton-Raphson. Para matulungan ko yung code na mas mabilis siya mag-run, gusto kong piliin si U0 at saka si V0 in a nice way. Kasi nga, hindi always guaranteed na nagko-converge yung Newton-Raphson method. Dapat yung initial condition, piliin mo to be close to the roots that you're looking for. Okay? So, dahil ayokong manghula lang ng initial guess, I want to do it in a smart way para hindi ako mag-aantay kung magko-converge siya or hindi. Okay? So, tingnan ko yung graph ni P. Pag ginraph ko si P, ito yung makikita ko. And now I can observe that there are roots that are near negative 2 and near kay positive 2. So that means kung root si negative 2 or may root na malapit kay negative 2, so merong factor na malapit kay x plus 2. Tapos dahil may root na malapit kay 2, merong factor na malapit kay x minus 2 by the factor theorem. So I'm thinking that x plus 2 times x minus 2 will be a good starting estimate for a quadratic factor. So pag pinag-multiply ko yan, makukuha ko ay x squared minus 4. So that's what I'm going to use as my initial guess. I will use as initial guess u sub 0 equals 0 and v sub 0 equals negative 4. Okay? Para lang matulungan ko yung method. But of course, you don't need to do this. You can just give an arbitrary U0 and V0 and cross your fingers and pray na mag-converge yung Newton-Raphson. Makita nyo naman kung di siya magko-converge by looking at the first few iterates, all right? Or hindi talaga matatapos yung iteration nyo, all right? Pero to give it a little push, so magandang starting conditioning pipiliin ko, all right? That's how I get these two initial guesses. Tapos ito na yung mangyayari. Ipa-plug in ko siya kay Bairstow's. Okay. So ito yung u sub 0, ito yung v sub 0. Tapos I let Bairstow's algorithm to run. Ang kagandahan kay Matlab, hindi siya masyadong sensitive pagka meron kang division. Alright? Nagkaroon ako ng division by 0 dito sa relative jump kasi pag-compute ng relative jump, this would be this guy minus u0 divided by u0. But my u0 is 0, so sabi ni Matlab, nagkakalokohan. Division by 0, pero that division by 0 will be will tend to infinity. Kasi nga meron akong constant divided by 0, this will be a very humongous number. All right, so positive infinity. Pero dahil definitely infinity is greater than the epsilon that we set, ipapagpatuloy ni Matlab yung iteration. Okay? Ganun, wala namang malaking problema kay V sub n. And after 5 iterations, nag-converge yung Newton-Raphson iteration. Okay? So ito yung nakuha kong UN, ito yung nakuha kong VN. So sabi ni Bairstow, okay, ito isang good approximate para dun sa quadratic factor. X squared minus 0.15, x minus 3.14. Okay? Tapos, dahil I am expecting this to be a good factor, then pag nag-quadratic formula ko dito, itong dalawang roots na makukuha ko would be a good estimate for the roots of the function p. Alright? And true enough, nung dinouble check ko, pinuha ko yung function value nito, at saka function value nito, order 10 to the negative 15 yung una, tapos eksaktong 0, up to machine precision, 0 yung function value nito. So indeed, after 0.01 second, I already got 2 good estimates. Dalawa kagad yung nakuha kong estimates. Okay? Now, para makuha pa yung natitirang dalawang roots, magde-deflation ako ngayon. Kesa manghula, magbigay ako ng U0 at V0, kasi pag nagbigay lang ako ng U0 at V0, okay, posibleng ito na namang dalawa ang makuha ko even if they are not of multiplicity 2. Alright? So kaya ang gagawin ko, magde-deflation na lang ako. Meron na akong alam na quadratic factor, so ang gagawin ko kay Matlab, okay, gawin mo yung P over Q1. Yung Q1, yun yung estimate na nakuha natin para sa quadratic factor kanina. Tapos nung pinagawa ko to kay Matlab, ito yung nakuha ko. Quadratic na siya. As expected, kasi quartic lang naman yung pinagsimula natin. Tapos, nag-quadratic formula na lang ako dito, tapos nakuha ko ay dalawang complex roots. This guy and this guy, complex conjugate pairs. And these two are two nice roots kasi nga ang order ng function values nila ay 10 to the negative 16, which is virtually 0 from a computer's point of view. Okay? All right, so does that make sense? Okay ba yung example? All right, so puntahan naman natin ngayon yung Matlab code. Siguro ito yung pinakahihintay nyo. Okay, so double check ko lang kung ready na yung Matlab ko. Okay, yeah. To experience the coding process, so explain ko lang. Huwag nyo lang basta i-screenshot to tapos i-copyhin, all right? I want you to understand every line of the code that I wrote. Let's see. Share ko yung Matlab screen ko. Okay. So I hope you guys are seeing my Matlab screen now. Kita na ba? Mukhang di pa, no? Let's... Bakit ganun? Now, I think you can see my Matlab screen. Okay ba yung font size? Or masyadong maliit? Okay, from my tablet mukhang okay naman siya. So, keep ko siya. Sabihan nyo lang ako kapag ka masyadong maliit. Okay. So, here's Mueller's method. Sorry, hindi pala Mueller's. Bakit Mueller's? Bairstow's. Pero ang tinawag ko sa kanya ay Newton 2D. Dapat pala Bairstow's yung ginawa kong title. Okay. So, gawin ko yung example 4.4 to illustrate. Okay. So, usual clear para walang variables na naiwan from previous runs. CLC para ma-clear yung command window, mawala yung display from previous estimates, from previous runs. Tick para masimulan yung timer. Initial guess, okay? Now, puntahan yung example 4.4. Siguro ito yung i-illustrate ko. And sa example 4.4, meron ng x to the 6 minus x to the 4th minus x cubed minus 1. Okay? So, yun yung polynomial na gusto kong hanapan ng root. Tapos dun sa module, pinag-graph ko kay Mathematica yung function s. Alright? Yung x to the 6 minus x to the 4th minus x cubed minus 1. Tapos nakita ko may root na malapit kay -1 at may root na malapit kay 1.5. So that means I know that x plus 1 times x minus 1.5 would be a nice initial estimate for a quadratic factor. So pag minultiply ko yung x plus 1 at saka x minus 1.5, I'm gonna get x squared minus 0.5x minus 1.5. Kaya yung initial guess ko, tinawag ko siyang u, negative 0.5, tapos initial guess ay negative 1.5. And then I need to declare in my code, line number 7, ano yung degree ng polynomial na kinoconsider ko? Yung sa example 4.4, degree 6 yung polynomial. So kaya n equals 6. Tapos kailangan kong ilagay yung coefficients. 'Di ba? Kailangan ko yung a sub i's. So para makuha yung a sub i's, kailangan kong i-encode ito. Buti hindi ko siya nabura. Copy paste na lang. Ang isang problema, posible maging complication kasi si Matlab ay ang indexing niya laging nagsisimula sa 1. All right? Ang count niya ng vector laging nag-start lang sa 1. Right? So hindi pwedeng magkaroon ng a sub 0. All right? So ibig sabihin itong a1 para hindi na ako mag-a-adjust dun sa mga formulas na nandun sa module, ang ginawa kong trick, so yung a1, siya pa rin yung coefficient ni x to the 1. Tama ba? Ito nga ba yan? Parang mali na siya. Wait, double check ko lang . Yeah, okay. So ito yung x to the 1, which is ito yung coefficient ni x to the 1, which is 0. Coefficient ni x2 siya yung a2, alright, which is also 0. And then kay s, balikan nyo si s, example 4.4, meron siyang negative x cubed. So yung a3 dapat siya ay negative 1. Okay? Then this is the coefficient of x to the 4th, x to the 5th, and x to the 6th. Alright? Tapos kailangan kong i-manually encode ano si a sub 0. Ano yung constant? Yung constant ay negative 1. So lagay ko lang siya dyan. Alright. So pag kailangan ko ng a sub 0, tatawagin ko na lang si a0. Wala na siya dun sa vector a. Para lang madali. Okay? Tapos remember, dun sa two-dimensional Newton-Raphson method, vector yung pagko-compute ng bawat iterate. So, inilagay ko lang sa loob ng vector u, si u at saka si v na initial conditions. Okay? Tapos column vector yung ginamit ko. So, kaya semicolon yung nagdi-divide between u and v o yung nasa pagitan nila, yung nagse-separate sa kanilang dalawa. Okay? Tapos tolerance 10 to the negative 6, yun yung sabing epsilon na gamitin. Maximum number of iterations 100. Tapos fprint para dun sa table, alright, header ng table. Fprint para dun sa initial values. So look at this, my initial u is u of 1. That means the first entry in vector u. And my v sub 0 is the second entry in the vector capital U. Right? So dinidisplay niya lang yan. Tapos, ito na yung formula 4.11. 4.12. Yung b of n ay equal kay 0. Yung b sub n minus 1 ay equal kay 0. Yung f of n is equal to 0. At yung f of n minus 1 ay equal kay 0. First line ng example, ng equation 4.12. So, in-encode ko siya dyan. Alright? Hindi yan nababago. Kahit mag-for loop tayo, mag-ilang iteration ng Newton-Raphson, lagi silang 0 by design. So, nasa labas na siya ng iteration process. Okay? But remember, you need to declare n before computing this, guys. Alright? So, si n, naka-declare na sa taas, yung degree. So, well-defined na to. Okay? Initial value for error, para lang alam niya na hindi siya mag-stop sa unang iteration pa lamang. Then I'll set iteration equals 1. So this is the first iteration. Tapos ito na yung meat nung algorithm. Okay? Yung nasa do while. So I asked Matlab to do this thing, yung nasa loob nung lines 27 to 49, while the error is greater than the tolerance and the iteration number is less than the maximum number of iterates. Okay? Tapos, ito yung mangyayari. So si u old for for recording purposes, sinet ko siya to be U. Alright? Para alam ko na, para hindi siya natatabunan. But before ako mag-iterate, nakasave na yung old. Kasi kailangan ko yung old iterate para dun sa jump criterion. Alright? Para computein yung criterion. So, yung U old, siya si U mula dun sa previous step. Okay? Tapos, yung lines 30 to 33, eto naman yung second and actually sila yung nasa second line ng equation 4.12. But note here na yung for loop started at j equals n minus 2. Mag-i-increment siya ng 1, ng negative 1. So pababa siya ng pababa hanggang marating niya si 1. Okay? Kasi nga hanggang b sub 1 at saka hanggang f sub 1 yung kayang i-compute ni Matlab. Hindi ko kayang ipa-compute sa kanya yung b sub 0 at saka f sub 0 sa loob ng for loop na to. Alright, hindi ko kayang gawin yung iteration hanggang kay 0 as what the module wanted because ang indexing nga ni Matlab nag-start sa 1. So walang b of 0 kasi yun yung 0th entry sa vector b. That doesn't make sense for Matlab. So nag-start siya lagi sa first entry. Okay? So kaya pinagawa ko lang to starting from n minus 1, every step it will go one value down hanggang makarating kay 1. Tapos minano-mano ko na lang yung computation ng B0 at saka ng F0. Okay? So now we have the complete set of the BKs and the FJs or the BJs and the FJs. So pwede ko na i-compute yung CD, yung CG at saka DH. Ito yung last two lines ng example 4.12. Okay? Tapos yung line 42, ito naman yung equation 4.15. Talagang copy-paste lang siya dyan. Alright? Just take note how to encode a 2x2 matrix in Matlab. Okay? Tapos yun na yun. Yun na yung next iterate. Na-compute nyo na yung bagong iterate na U. Tapos i-check ko ngayon ano yung relative jump para malaman ko kung titigil na ba tayo. So kukunin ko yung U old minus U. Okay? So na-save ko na naman yung U old. Yan yung previous result minus U result. But mind you, this would be a 2x1 vector minus a 2x1 vector. So we get a 2x1 vector. Okay? Tapos, ang kagandahan kay Matlab, pwede niyang kunin yung absolute value o yung modulus. Kay Matlab, yung absolute value at saka modulus parehas lang. So it doesn't matter if you old and you have complex entries, kayang kunan ng absolute value ni Matlab yon kahit complex yung laman nila, which is the usual modulus. Okay? So kunin mo yung absolute value ng isang vector. Ano ba yung absolute value ng isang vector kay Matlab? Yun yung kagandahan kay Matlab kasi it's designed for matrices. Kaya nga Matlab yung pangalan niya, it's Matrix Laboratory. Okay? So pag kinuha mo yung absolute value ng isang matrix, ibibigay niya sa iyo yung matrix na ang laman ay mga absolute values ng entry ng original matrix. So yung U old minus U, ang laman niya, o yung pag kinuha ko yung absolute value, 2x1 vector pa rin, pero ang laman niya ay absolute value nung nasa U old minus U. Okay? Ganun din, kunin ko yung absolute value ng U old. Tapos, gumamit ako dito ng dot divide. Okay? Pag gumamit kayo ng division sa matrix, i-multiply niya yon by the inverse nung divisor. Okay? Pero dahil gusto ko ay term by term division, kailangan dot divide yung gamitin ko. Ibig sabihin, yung first entry dun sa numerator, i-divide niya ng first entry by the denominator. And what will that represent? That will represent the relative jump on U. Okay? Kukumputin niya yung uj plus 1 minus U all over j absolute value. Okay? Tapos, kukunin niya yung second entry nito, i-divide niya by the second entry of this guy, you will get the relative jump for the VJs. Alright? So parang shinortcut ko lang to para isang line lang yung pagko-compute ng dalawang error thresholds or ng dalawang relative jumps. Tapos dahil gusto ko na parehas silang makasatisfy nung tolerance, isa-set ko yung error to be the maximum jump vector. Kasi yung relative jump, siya ay 2x1 vector na laman niya yung relative jumps kay U at saka relative jump kay V. Okay? Pag kinuha ko yung max ng isang vector, ibibigay niya yung pinakamalaking value or pinakamalaking entry ng vector na yon. So, kukomputin ni Matlab ano yung mas malaki dun sa dalawang entries ng vector na relative jump, and we'll set it to be the error. Okay? So, ito yung mas malaking relative jump. Remember, gusto nating itigil kapag parehas na relative jumps ay less than epsilon. So, sure ako kapag yung maximum ay mas maliit na sa tolerance, so ibig sabihin na satisfy ko na yung error threshold. So, ito na yung mangyayari dito. Yun yung i-check ni Matlab dito. Alright? And then, pagka natapos na yung iteration, ito na. Papaprint ko na lang ano yung quadratic factors. Tapos, makukuha ko yung quadratic factors, kailangan ko ngayon i-apply yung quadratic formula para mahanap yung roots corresponding to that quadratic factor. So, tinawag ko lang na QA, yung A dun sa quadratic function, si QB yung coefficient ni X, si QC yung coefficient ni, ito yung constant, right? But remember, our factors of the form x squared plus u, x plus v. Alright? Tapos, quadratic formula lang yan. So, makukuha ko na yung roots. Tapos, ipapakompute ko ano yung absolute value nung function value ng mga roots para ma-check na maganda yung estimate ko and so on. Alright? And that's it. That's my code for this guy. So before proceeding, do you guys have any questions about it? Does my program make sense? Siyempre, hindi ko pala nakikita yung reactions nyo kasi naka-share screen ako. Panoorin ko na lang dun sa sa tablet ko. All right? So I hope my program makes sense. Okay. Now, sige, i-run natin. Tingnan natin kung ano yung ibibigay niya. Okay, so run ko lang yan. Okay. And I hope this is the one that is on the handout. Dapat tama yan. Okay, let me see. Okay, there you go. Nagmamatch siya dun sa result dun sa module. All right. So we got this quadratic factor. Nagpa-quadratic formula ako dyan. Nakuha ko yung dalawang roots. This guy and this guy. All right. Sila yung mga roots nung or estimate para dun sa roots nung ating original function s. Tapos ang magnitude nung function values nila ay 10 to the negative 15 at 10 to the negative 15. So we're good. We have good results in here. Okay? Now, paano ko gagawin yung deflation? All right? Meron ka ng quadratic factor. So, punta ako dun sa isa ko pang program, ang tawag ko sa kanya ay deflate. Okay, dun sa deflation, okay, kailangan ko yung function ko na i-deflate. Wait, copy-paste ko lang to. Marami kasi akong pinaglaro ang functions kaninang umaga para ma-check kung tama yung program ko. So, or hindi ko alam kung para sa exerbat or what. Okay, yeah. So, deflation program naman. Okay, para hindi kayo magmamano-manong synthetic division or long division. Okay. Now, we want to work with symbolic variables here. So, start your deflation program by sims x para alam ni Matlab si x ay treated to be a symbolic variable. And then I will define my function f, the function to be deflated. Okay. So, x to the 6 minus x to the 4th minus x cubed minus 1. Yan yung s of x natin sa example 4.4. Okay. Tapos line 4, ito yung divisor na na-compute natin mula kay Bairstow's method. Okay? So remember, ang form ng quadratic factor na binigay sa atin ni Bairstow ay x squared plus ux. So kinol ko na lang, wala akong clear dito para pwede kong magamit yung mga results mula dun sa previous program na ni-run ko. Pag naglagay ka dyan ng clear, mabubura yung U1 at saka yung U2. So dapat i-save mo siya sa papel or i-copy-paste mo muna siya sa notepad, tapos ibalik mo siya rito. Alright? Pero ayokong gawin yun, di na lang ako nag-clear. So para ma-call ko si U1 up to all the decimal digits stored by Matlab in the previous run. Okay? times x plus u2. So ito yung u at saka v na final mula dun sa Bairstow's method. Okay. Tapos paano natin ipapagawa kay Matlab yung division? So una, dapat symbolic variable muna. Kaya sims yung ginamit ko. Tapos maganda yung code, ito lang. Gamitin nyo lang tong line number 9. So yung routine ay built-in, ang tawag ay polynomial reduce. So type polynomial reduce, this is case sensitive, small p in polynomial, capital R in reduce, okay? Tapos of what? Ang inputs niya ay the dividend, tapos comma, yung divisor. Okay. Tapos ang ibibigay niya sa atin ay isang vector. Nang laman ay si R at saka si Q. Sino si R? Si R yung remainder, si little q siya yung quotient. Okay? Yun yung output ng polynomial reduce. Kaya lang, ibibigay sa akin ni Matlab ay symbolic value. So exact yung computation niya. Mga fractions or mga mahabang decimals yung ibibigay niya sa akin for R and for Q. Kaya ang ginawa ko, sa line 11, gusto kong makita na lang yung parang floating point representation ni Q. So I let capital Q to be equal to the VPA form ni little q para hindi siya symbolic form. Okay? Tapos yung lines 14 to 15, para lang ma-check kung tama yung pagkakagawa ni polynomial reduce, but you can comment this out. Hindi naman siya mahalaga. Sure naman tayo na tama yung polynomial reduce. Sanity check ko lang yung 14 and 15 para ma-check kung tama yung polynomial reduce. It is correct, so you don't need to check it anymore. Tapos, okay, siguro, ano ko muna to? Let me comment this out. Tingnan muna natin yung results nito. Okay. So I'll run the deflate algorithm. Okay. All right. Nag-run na siya. Wala siyang output on the command window kasi wala akong pina-output sa kanya. Pero if I ask it to output Q, ito yung ibibigay niya. Okay. So I hope nakikita nyo si Q dun sa ilalim. So ito yung okay. So ito yung deflated polynomial. Remember, we started with the polynomial of degree 6. Dinivide ko siya by the quadratic factor we got from Bairstow's. So naging quartic na lang yung polynomial. Okay? So naging x to the 4th na lang siya. So hindi nyo kailangan na gawin ito mano-mano. So pwede nyo ipagawa kay Matlab using the command okay. Hindi ko pa pala pwedeng ipagawa yung line 17 to 28. Kasi ito yung quadratic formula implementation. Hindi pa makapag-quadratic formula kay x to the 4th kasi nga ano siya, quartic polynomial pa siya. Alright? So hindi pa mag-work yung quadratic formula. So ang gagawin ko ngayon, magbe-Bairstow na naman ako para kay x to the 4th plus 0.4 x cubed and so on. So ito naman si Q, siya yung i-output ko kay Bairstow. So ika-copy-paste ko yan. Okay, copy-paste. Hopefully na-copy-paste. Pupunta ako kay Bairstow's algorithm. Siya na yung bagong polynomial na paglalaruan ko rito. So yung coefficients nung polynomial Q na yon, siya naman yung ilalagay ko dito kay A. Tapos siya rin yung na kay A sub 0. And then tapos syempre papalitan ko na rin yung N kasi degree 4 na lang yung polynomial natin. So papalitan si N, mapapalitan yung A, mapapalitan yung A sub 0. You can again shop for nice U0 and V0 by plotting yung deflated polynomial Q natin. Pa-plot nyo siya. Or pwede rin naman kasi ang laki nun chance na magko-converge siya. So ang ginawa ko yata dun sa handout, hindi na ako nagpa-plot for a second time for the deflated polynomial Q. Ginamit ko na rin yung same initial guess, negative 0.5 and 1.5 yata para dun sa second round ng Bairstow's algorithm. And nice enough, nag-converge pa rin yung method, nakakuha ko ng ibang roots. Yun yung kagandahan sa deflation. Kasi natatanggal mo na yung mga roots na hindi na nauulit as roots. So pwede ko nang ulitin yung same initial condition and I will get a different set of roots. Okay? Kapag ka nag-output siya tapos parehas yung roots na nakuha nyo from your previous run, that means that root that you got is of multiplicity 2. Alright? So valid pa rin siya. So makakount mo pa rin siya, mababawas mo siya dun sa total number of roots promised by the fundamental theorem of algebra. Okay? So kasi nga pwedeng halimbawa, meron kang x plus 1 quantity square, x minus 1 quantity squared na factor. So ibig sabihin si 1 ay mag-appear as a factor of your polynomial of multiplicity 2 or a root of multiplicity 2. So twice mo makikita si 1 dun sa Bairstow's algorithm. Twice siya mag-appear. So kung nag-deflation ka, sure ka na pwede mong tanggalin si 1 twice doon sa total number of expected roots. Pero kung hindi ka nag-deflation, hindi mo pwedeng masabi na twice mo tatanggalin si 1 kasi multiplicity 2 siya. Hindi ka magiging sure na multiplicity 2 siya unless gumamit ka ng deflation. Alright? So the rest, copy-paste na lang. Mapapalitan si A, mapapalitan si A sub 0, but I think that's it. You run your algorithm again, you'll get a different set of quadratic factor, a different quadratic factor. Tapos, dahil makukuha mo rin ay quadratic, kailangan mo pa mag-deflate ng isa pang beses, and then you will get, after the second deflation, a quadratic polynomial whose roots can easily be obtained by using the quadratic formula. Okay? So I guess that's it. Do you guys have any questions? Thank you for staying. Medyo clingy na tayo sa isa't isa. 30 minutes na tayong way beyond time. But thank you for staying. And I hope this extra session will help you on the lab extra on Monday. Okay. Now let me stop sharing that and let me go back. Sulitin ko na hanggang 1:30. All right. Tingnan lang natin yung lab exer. Pabilis lang. Meron ako ditong extra exercise for you guys to try out. Oops, may typo. Dalawa yung I. Isa lang siya dapat. Okay. All right. So this would be your lab exercise. It's a little bit, what you call this? A little bit deceiving kasi ang iksi, dalawang problems lamang. Kaya lang, again, the bulk of the work will be on the programming side. But I hope this session helped you or gave you an idea how to do the programming. Okay? So kung na-lost talaga kayo or hindi kayo familiar kay Matlab, you can go back to the recording, screenshot my code. Pero sana pag kinode nyo siya, naintindihan nyo kung para saan yung bawat line ng code. Okay? Kasi nga sa problem sets and for future exercises, I will test how well can you modify or you can work around with the code that you have written. Okay? Huwag nyo i-delete yung mga codes na sinulat nyo kasi most likely gagamitin natin yan in future assessments. Okay? So, gagamit kayo ng Mueller's para sa number 1. Tapos, gagamit kayo ng Bairstow's para sa number 2. And that's simple. Mueller's and Bairstow's with deflation. Okay? But the only difference here is I wrote here explicitly that you need to show me all the iterates. Okay? Nung routine. Gusto kong makita kung tama ba yung program nyo. Alright? Or kung nasulat nyo ng tama yung program. So, kailangan ko makita yung mga iterations ng routine. Okay. So, dun sa Mueller's, ilan nga ba? Siguro magdadalawang deflation kayo sa Mueller's. Actually, depende pala sa initial guess na ibibigay nyo. So, you can give your initial guess, alright? You'll be lucky if sa Mueller's ay complex yung makuha yung root at the first iteration. Kasi kapag complex yung, or actually hindi complex, kung non-real, yung makukuha nyo na unang solution mula kay Mueller or unang estimate mula kay Mueller, sure, pwede kayong gumamit ng conjugate root theorem na yung conjugate na nakuha yung root ay root din. So that means makakakuha ka kaagad ng quadratic factor para sa x to the 4th. So ibig sabihin, isang deflation lang yung kailangan mo. I-divide mo lang to by the product of those linear factors that you got from the conjugate from the complex conjugate pair of roots. Tapos quartic to divided by quadratic, so magiging quadratic na lang siya, quadratic formula. Kung medyo minalas ka, tas puro real yung nakukuha mo na roots mula kay Mueller, so kailangan mo mag-deflate twice. So x to the fourth, i-divide mo by x minus the real root that you got. You'll get a cubic polynomial. You'll run Mueller's again, okay? And then you deflate one more time, but deflating a cubic by a linear will give you a quadratic. So dun sa quadratic, pwede ka na mag-quadratic formula. Wag mo nang i-run si Mueller uli. Pag quadratic, mag-quadratic formula ka na lamang. Alright? So yon, ganun yung work nyo for number 1. So number 2, I guess it's straightforward yung Bairstow's. So at every step, you'll get 2 roots, alright? Tapos mag-deflate ka, magiging quartic siya. So kailangan mo uli mag-Bairstow's. Makakakuha ko uli ng quadratic, i-deflate mo uli siya, magiging quadratic. Pag naging quadratic na siya, ay quadratic formula. So the nice thing about that is that we are getting two roots or 2 estimates at every run of Bairstow's. Tapos ang bilis nga ng Bairstow's kasi dalawa na kagad at any given time yung binibigay niyo ng roots, tapos yung convergence pa ng method ay quadratic, na inherit niya kasi nga yung Bairstow's is just an extension of the Newton-Raphson in 2 dimensions. Okay? So I think that's it. Any questions? Okay, so if there are none, again, I appreciate you staying way beyond time, 30 minutes beyond time. So thank you, everyone. So enjoy the weekend. Good luck sa mga nagwa 155 and good luck everybody kasi medyo mahaba-habang programming ito, not like Newton-Raphson or the secant method last time. That's why I opted to show you my code, all right? So just make sure you understand every part of the code, you understand the method, kasi definitely sa problem set, babawi ako, all right? I'll ask you to elaborate on those codes or on those methods itself, all right? So with that, thank you guys. Enjoy the weekend. Kung makakapag-weekend kayo, I know you have lots of things to do. So we have some events on Monday that you can get points for. So, and then may klase tayo sa lab on Monday. All right? So, bye guys and keep safe. Have a good one. All right. And meeting pa na.